Good afternoon, Excellencies, distinguished guests, dignitaries, friends, colleagues, professionals, practitioners, and the large dams community. I'm honored to be invited to address your conference on behalf of the International Commission on Irrigation and Drainage, ICID. Why ICID actually is interested in dams and the reservoirs? ICID has a register of historical water structures, including dams and reservoirs, and has interest in dams and reservoirs as they provide steady water supply for drinking and irrigation all over the year, protection against extreme events such as flood, guarantee steady water supply during extreme events of droughts, provide hydropowers for irrigation systems, abstraction pumps, dairy farming, and agricultural production in general, fish, wildlife, and natural healthy and rich habitat, and steady flow for the whole year, enabling us to apply integrated water management. Dams and reservoirs are of great importance to ICID as irrigation consumes 70% of the global freshwater resources. For thousands of years, dams were built by early civilizations and have ensured adequate supply by storing water in times of surplus and releasing it in the time of scarcity, thus preventing mitigation and the floods. And you can see here how dams 3,000 years BC were built in Egypt, for example, and they have been, of course, from moving and developed from simple to large and complex, and from single purpose to multi-purpose dams. The same actually noticed also in Japan. They built dams in the 1st century or before, and then these dams, of course, moved from simple and single purpose to multi-purpose dams. The current challenges that we have right now is that by 2050, we are increasing as a population from 6 to 9 billion. Subsequently, the food demand is expected to increase by 100%, and irrigation consumes 70% of the freshwater resources. Water consumption is expected to increase by 50%, increase in global energy demand by 30 to 40%, and we have to know irrigation requires a huge amount of energy. Climate change predicted increase and reduced rainfall in different parts of the world, subsequently reduced runoff, river flows, and groundwater recharge. The future climate change predicts more frequent extreme events of flood and drought, and irrigation requires steady water supply throughout the year. Currently, there is an increase in the gap between water supply and demand, and by 2030, we can expect 40% overall gap between the supply and the demand. So do we need more dams and reservoirs to meet the challenges? To answer these questions, we need to ask ourselves the following. Do we have adequate water supply to meet the demand now and in the future without extra dams and reservoirs? Can we cope with the climate change extreme events of flood and drought now and in the future without more dams and reservoirs? Can we meet the energy demand now and in the future without extra dams and reservoirs? Before answering those questions, let us have a look at the impact of population increase, climate change, and the others on water resources. So population increase in 1950, you can see here the number of population represented by those bright circles in 1950 hardly was really much population, and that increased from 50 to 2000, 2015 to 2020. As you can see now, the bright circles increased tremendously over the years, and that was reflected in the share of per capita fresh water from 1950, 12,000 cubic meter to expected 4,500 cubic meter by 2050. And also we noticed in our work in different parts of the world, the groundwater depletion and exhaustion of the groundwater is taking place already. And this is example from island of Crete and in the Guadiana Valley in Spain as well, and also in some parts of the world, including the Gulf countries. And you can see here, United Arab Emirates, Qatar, Saudi Arabia, and other countries where the recharge actually is, the abstraction rather, is 1,200 times the recharge level. So this is really a high exploitation of the groundwater took place. And these areas, the groundwater is really hardly renewable. Climate change impact on water supply and demand. And I will show you here some work in Italy, Brazil, and Cyprus and the UK. And the gap here that we estimated for Cyprus shows that there's a huge gap, and that gap is widening with time between the supply and the demand. Similar in Italy, especially south of Italy, we also found that there is a widening gap between water supply and demand, whatever scenario we try. And here in the UK, we tried to look at the water supply and the demand gap in several catchments from northern Scotland all the way to Fowey and Cornwall. And I will just show one catchment here, Don catchment in the Midlands. And here you can see the stream flow or the river flow there is actually decreasing, especially in the summer where irrigation is needed mostly, and increases with time and with high emission scenario. The groundwater as well recharge is decreasing with time, and also with the high emission scenarios, especially in summer where we mostly need irrigation. And looking at the drought events on those also catchments in the Don, like other catchments, we noticed the number of drought events is likely to increase, the frequency would increase, and the severity would increase also with time and with the emission scenario, high emission scenario in particular. So this is the gap here between supply and demand and the Don catchment in the Midlands, but we found similar gaps in different parts of the UK, apart from Scotland in Eden catchment and North. There's some publications here. And how to narrow the gap, and we have different ways to do it. The engineering side, of course, more surface storage, new reservoirs and dams, more groundwater recharge, more wells, use of treated wastewater and brackish saline water, and desalination of seawater. However, desalination can only be economically viable if we irrigate cash crops. There are some other solutions like improving water use efficiency, and of course, using a more efficient irrigation system and suitable crops and rotations. So to increase the water supply, we can actually increase water supply at different levels and different scales, from small to meso to macro. And you can see here, we started at a very early stage by harvesting water in check dams, in field ponds, rural urbans, and this is example from India. And another example of mesoscale mountain lakes like North African. And then of course, the large and multi-purpose dams like the one of Three Georges in China. And we also can harvest water underground dams, like the example here of Brazil, where they dig a trench and they put a plastic sheet and different sections, and when the water falls, it will remain within the section. And also you can direct the runoff into vertical shafts to the groundwater, as that example also from India. So you can also increase the water supply through the groundwater recharge. Issues related to dams and the reservoirs, the safety, the societal impact, environmental and ecological impact on local climatic conditions like cloud formation, impact on downstream riparian countries in shared rivers, impact on river flows and navigation and evaporation losses. Building dams and the reservoir is not only civil engineering, and we have to keep that in mind. It's not only civil engineering construction business, but it requires good knowledge about hydrology, economy, environment, and societies. In terms of hydrology, we need to consider the long-term historical records of flow, understand the temporal variations, and avoid using long-term mean values if extreme events are frequent or expected. And we have been looking at those actually uncertainty levels, and we applied two ways of looking at the safety, and one of them is estimation of the volume of the reservoir that has minimum risk and the low probability of failure by conducting the probability of failure test analysis. And also we conducted uncertainty analysis of river flows, and that's actually from days to seasons and to annual. And this example of probability of failure that we conducted at some stage, and we can actually select a volume of the reservoir that would actually allow us to have less risk and less probability of failure and higher success rate. So you can economize on the digging costs, but you will also increase probability of failure. And we have seen that in some dams, and especially those were built not taking into account the extreme events, and where there was some destruction of those dams, and we have seen one recently in Brazil. They are overtopping and then they collapse. The uncertainty analysis of river flows, we applied generalized likelihood uncertainty estimation, they call it GLUE, and the model can capture the percentage of the observed river flow or containment ratio, CR, that are contained in the 5 to 95 likelihood weighted quantile envelope. This is here an example of the calculations we do for the river flows on monthly and daily and annual. And here you can see in that Don catchment in particular, the containment ratio, the observations between the 5% and 95% likelihood quantiles can be 57% if we are looking at the daily flows, because it fluctuates a lot. And then monthly, that aggregates more the daily, and then you can have containment ratio of 70. So you have less uncertainty here. When you talk about seasonal, the uncertainty, of course, get less. And when you apply for annual, where all the variations is aggregated, and you have more smooth curves, and you can have a containment ratio of 85% and less uncertainty. However, these actually important if you are building a dam, and for safety of the dam, you might not consider the annual flows. You might have to consider sub-annual, monthly, or seasonal, and in order to avoid the risk of being overflown, especially the reservoirs over the top of the dams. And here's a number of applications. Sediment issue, also it has been referred to by Dr. George Anadel, and sedimentation control of the reservoir by sediment flushing, sluicing, or dredging must be supported by erosion control in the watershed in order to prolong reservoirs' life. Investment in erosion control is to be encouraged, and continuous desiltation is necessary to prolong the lifetime of dams and reservoirs. There are some issues related to dams and reservoirs of shared rivers, especially ICID has already established a task team on transboundary waters, as they provide 40% of the world population and 60% of world food production. And there should be agreement, and the regulations of building dams over shared rivers should be in place before building the dam to avoid negative impact on downstream communities. And we have a good example here in Europe, the Danube River, which is shared between 10 countries, and they have already agreement took into effect in 1998. There are some societal issues related to dams and societal impact on local communities during and after the building of the dam. By moving them to new areas with possible change in land use and the landscape, their economy and traditions are affected. We must ensure that they are better off after dam and reservoirs building. There are some environmental issues as well. Change in local climate, new microclimate due to the cloud formation over the reservoirs, such as what happened in High Aswan Dam area. Ecological impact on wildlife, including fish migration, due to the change in the river flows, water depths, and water temperature. Balance must be struck between environmental impacts of development and environmental conservation served by the development. The evaporation losses from reservoir could be very significant. However, it is hardly accurately quantified and reduced. And if we look here at the efficiency for irrigation, it starts at the reservoir by 70% because we lose a lot of water at that stage at the reservoirs level. And here there is an example from the UK where farmers, they cover the reservoirs by floating solar panel to produce electricity for the farming activities, and also they release some of it to the national grid. And we use for that large scale evaporation measurements, we use centimeters, and centimeters can measure the actual evaporation over a stretch of 10 kilometers stretch. And management issues, good maintenance and operation system is essential for dam safety. The need for regulations to control water harvesting into unauthorized reservoirs, as these negatively affect the flow to rivers and dams. Multi-purpose dams and reservoirs for water and energy security is preferred over single-use dams and reservoirs. Intensive 4-month rain monsoon in some Asian countries requires a suitable design, operation, and the maintenance system, and the holistic integrated water supply demand management to ensure steady water supply over the whole year. There is a need to raise awareness of the benefits gained from dams and reservoirs in terms of water and food security, society welfare, income, leisure, and tourism, and the local regional economy, while safeguarding the environment and ecological service. So do we need more dams and reservoirs? The answer is yes. In the future, we will need to increase water supply by increasing rainwater and runoff harvesting and store the water in reservoirs, and the reasons are: in order to meet the current challenge of population increase, while water is limited, we would need to double the food production by 2050. This needs extra water supply. The future climate change predicts more frequent extreme events of flood and the drought. Irrigation and the food production requires a steady water supply throughout the year. Energy use is likely to increase by 30 to 40% by 2050, and we need multi-purpose dams, reservoirs to produce renewable, clean energy, hydropower, to meet the energy demand and mitigate the greenhouse gas generated by fossil fuel. Thank you very much, and I wish you a very successful conference. Thank you.